hoping to see this live, we'll have to deal. Okay. So I will post this later on. Let's start tackling the Chatelier. That's actually a nice place to start since it builds all our concepts very nicely. Okay, let's try this, and I'll impose a number of different changes, and we'll just see which way it shifts. One thing to note is that if this is exothermic or less than 0, that means heat is a product. So we've got heat over here. So let's say just simple ones. If I add A, then it's going to shift to the right. If I added B, it's going to shift. Not at all. If I add, let's do a variant on this. If I add A, what happens to K? How does K change? Nobody said it so far. K doesn't change. It's a constant, remember, for the reaction. K doesn't change. But Q, I think most of you are thinking of Q. What would happen to Q? Q is product. If we added A, Q is products over reactants, and basically we're adding reactants. This would decrease. Okay, let's try some more. If I increase the volume, what happens? In this case, you have to look at the gases. There's the D, C, and A are all gases, and but there's 4 moles of D on the right and a total of 4 moles of C on the left. So there's equal number of moles of gas. There's no shift. So no shift if you increase or decrease the volume. What happens if I increase the temperature? If I add heat, and there's heat here, it has to shift to the left. Okay, because there's heat here already. I add more heat, it's going to go that way. Okay, that's about it that I have with Le Chatelier. Check. Cool. Let's move on. There's no questions? Yes? Say it again. Of what? Yeah, right now that's why the volume had no change. He's saying there's equal number of moles of gas on both sides. If there wasn't, okay, now there's not. So there's 4 here and 2 on the left. And so you increase volume, which way will it go? Increased volume has to go to the right-hand side where there's more. It's getting bigger, so it's going to go to the bigger side. If it was getting smaller, it'd go to the left-hand side of the smaller side. Okay, cool. Is that all right? All right. Yes? Oh. Yeah, you'd want to think, if I said this, it's the same as saying this. Pressure would be the opposite of whatever volume is. So I usually just figure out volume, and then I know pressure is the opposite. Okay, let's try some more stuff. Let's see, let's do some of this acid-base stuff up here. So if I give you a reaction, you should be able to label the acid, base, conjugate acid, and conjugate base. So if you want to work ahead of me, that's fine. But in just a moment, I'm going to label acid, base, conjugate base. If you don't want to, you want to try to first go ahead and then look up and see if you get the right answer. Okay? Let me see if I can think of another one while you're messing around. you could also write the products. I put a second one up here. You could write the products to it and write what's what. Okay, while you're thinking of the second one, whoever wants to work on that one, I'll explain the first. Here, NO2 minus grabs a hydrogen, and so it must be a base. It's a proton acceptor. Thus, the conjugate is the conjugate acid. And so, if NO2 minus is the base, H2O is the acid, thus OH minus is the conjugate base, which we should recognize OH minus as a conjugate base. Okay, so that's how you label those. Let's do the next one. I'll write the products here. You can look up when you think you've got it. And then I'll label everything. Alright, now let me explain it. You see, I chose the reaction for which HSO4 minus loses a proton to go to SO4 minus. That means a donated proton or is an acid. You could have written this as this HSO4 minus receiving a proton, but then that becomes sulfuric acid, and really it wouldn't go forward at all because sulfuric acid is such a strong acid. So really it's a better acid than it is base. So we've got an acid here, water's the base. If HSO4 is the acid, the one that lost the proton is the conjugate base. Water's the base, then H3O plus is the conjugate acid. Notice that usually the plus charges are the acids and the minus charges are the bases. Not always true, as you can see on this side, but it becomes actually more minus over here. Okay, any questions on those two? So I would not have written this. You can, I guess, but the problem is this is a really strong acid, so this would be the base acid, conjugate base. Here the base gains a proton, becomes conjugate acid. The acid loses a proton. But here really, because we have such a strong acid, this reaction goes 100% to the left because of the strong acid. So it's more likely that this would act as an acid. Okay, any questions identifying these? Yes. How do you know what to end with when you're writing the reaction? Okay, so when you're writing the reaction, if this is acting as a base, for example, then it receives a proton from what? To become this. Well, if water just donated a proton, there's nothing else it could be but OH minus. Now, if water acts as a base, as in this case, that means it's accepting a proton to become this. So it depends what this is, what water does. And so when this is a base, you'll get this kind of reaction. This is the general reaction for a base. When this is an acid, you'll get this sort of product, and this is a general reaction for acid. You can also have other kinds of reactions. For example, let's see. This kind of reaction. Here. This is more of a neutralization reaction, where we have a strong base and a strong acid. So I'll label this a base and an acid. And then you go to water plus a salt, in this case. So whenever you have a neutralization reaction, acid plus base goes to salt plus water. And we want to balance this. So I think we'll need 2 of those and potentially 2 waters. I think we'll do it. And so there's, remember, 4 types of reactions I showed you. The most common 2 types that we'll see in our class are general reaction for an acid and a base. The next common type is the one I just did, which is neutralization. The third, or the fourth most common, would be something like this. That would be the least common, but you still might see it from time to time. In this case, we're talking about Lewis acids and Lewis bases. What you'd want to recognize is there's a lone pair on that NH3, and it's a electron pair donor, which means it's a Lewis base, which we'll put Lb. This is electron pair acceptor, or a Lewis acid. So this lone pair right here basically grabbed the boron, and it forms this bond. So the lone pair became this bond right there. And so not always, but often, this kind of reaction will result in a complex that's just one entity. And so we don't really characterize this as anything. All right, that's the, let's see if I got all that stuff. I got some Lewis acid, Lewis base. So what you want to know about Lewis acid and Lewis base is that Lewis acid is electron pair acceptor, Lewis base is electron pair donor. So to recognize a Lewis base, you're looking for something with electrons on it, usually, like lone pair electrons are a pretty good sign, especially those lone pair electrons forming some sort of bond. Okay, that's that. All right, let's go to the next one. The next category we'll tackle is the one right under it, the acid, base, or neutral category here. Let's tackle acid, base, or neutral. Acid, base, or neutral. Okay. So you have this. You want to figure out if it's acidic, basic, or neutral. Eventually, you might be able to do this in your mind, but in the beginning, while you're getting used to it, look at each ion separately, and then write out its conjugate, and then identify it accordingly. So this is a strong base, so this is neutral. This is just a regular acid, so this is regular base. A neutral plus a base makes this basic. And in fact, what we would do if we did a problem was ignore the sodium because it's neutral, and we're just going to pay attention to F minus. So we don't pay attention to spectator ions. And usually, if you're not aware of it, take a look at the periodic table. Anything in the first two columns of the periodic table is usually a spectator ion, not including the ones at the top. So lithium, really all the way down to cesium, and magnesium all the way down to barium. Typically, those are spectator ions. And then on the right-hand side, again, the halogen column, right next to the noble gases, chlorine, iodine, those would be also neutral compounds or spectator ions. So you usually don't count the ones at the top and bottom might have interesting properties. So you can make up all kinds of these with your buddies. So that one. Okay? So then you go, well, that's NH4 plus, and this is NO3 minus. You've got NH4 plus, that's NH4OH, which you might know, that's the same as ammonia. And this conjugate is HNO3. So, get your other pen out. HNO3 is a strong acid, one of your strong acids. So this is neutral. Yeah, strong acid, so remember it's neutral. This one is regular base, so this is just a regular acid. So an acid plus a neutral, this is an acid. And NO3, that's a polyatomic ion that is useless for us. So we'd really pay attention to NH4 plus if we were doing a problem with this compound. So let's say, for example, in the top case, if I wanted to write a general reaction of this reacting in solution, then I would say, well, F minus plus H2O goes to HF plus what? OH minus. Remember, the water has to donate to this because it's a base. It's accepting the proton. Similarly, for this one, NH4 plus H2O, if that was reacting in solution, it would form NH3 plus OH minus. Oh wait, no. That sounds crazy. H3O plus. Yeah, this was an acid. It donated a proton to water to become H3O plus. Okay. So acid, base, or neutral, always separate them out into their ions and evaluate each one separately. Okay, not totally related to that, but on our next subject, we'll take a look at the inductive effect. It's a good one to do next, inductive effect. What happens is, and if I could do a little mini summary here, what you'll need to occasionally figure out which is the, say, stronger acid, and you'll have four means of comparison. That's electronegativity, polarizability, resonance, and the inductive effect, which is the one I'll explain more. But essentially, electronegativity and polarizability simplify out to this, that if you go this way and down on the periodic table, you become a stronger acid. That's what the first two. The next one says that the more resonance you have, the more likely you're going to be a stronger acid. So you're looking for a double bond, you're looking for triple bonds, and you're looking for lots of oxygens. If you see those, more likely there's resonance. The best thing to do always is draw the Lewis structure, but if you're in a hurry, that's what you'd be looking for. Okay, the inductive effect, you're looking for a fluorine or a chlorine, and these are typically on organic molecules. Things with carbons and hydrogens on them. So let me explain that one, because that one was where the question was asked. Let's say I have a compound like this. Okay. And remember, at each vertex is a carbon, and every carbon must have 4 bonds, so there's hydrogens all over the place here. Like that. Okay. Now, if this were an acid, which hydrogen would be lost? There's a lot to choose from. You want to lose this one. Why is that? It's one of these 4. I'm here waiting for one of those 4 answers. Electronegativity, because oxygen is more electronegative than carbon. So oxygen is more to the right on the periodic table. It can hold the negative charge better. So it's going to be, its conjugate base will be more stable, causing the acid, this, to be stronger. So this is the hydrogen you're expecting to lose, not any of these. And that'll be an okay acid. Now, if I erase this, and let's say I put a fluorine here. In that case, the acid has now become even stronger. So this fluorine here, again, stabilizes what would be the conjugate base, making this acid stronger. If I put another fluorine here, it'll even be stronger. Okay? Same will go for chlorine. So you're looking for fluorines or chlorines. It's related to their electronegativity, but we put it in a separate subcategory called the inductive effect. That basically, fluorines or chlorines can pull negative charge towards itself, stabilizing the molecule and making the acid strong. So that's the inductive effect that somebody asked about. Ready to move on? Which one would what?
Like if you were doing one with resonance and one with polarization.
What if we mix effects? Mix these 4 up. You wouldn't be able to solve that problem, so I couldn't give you that kind of problem where you mix them up. You'll see a difference that will be one of these 4 categories. Yeah. So this is what you're looking for. And take a look at the practice exams. You should see what I mean. I forgot to mention it. But You can, so I think I posted a few practice exams. If you're really weird and hardcore, you can get go through this and be crazy. But otherwise, look at the practice exams I posted. Whatever is most helpful to give you a good grade, that's what I always recommend. Okay, pKa, that'll actually be really quick. pKa. Tackle that. So remember, pKa is the negative log of Ka. If you have the general reaction for an acid, so an acid donates a proton to water, water becomes H3O+, Ka is then this. We don't include any liquids, so we're not including water. Okay, there's Ka. So you can plug that in to find pKa. All right, let's do a few things on this. If Ka is large, is the acid strong or weak? Strong. Ka is large, that means it's strong. Does that mean the reactants are favored or unfavored? Unfavored. Unfavored. Okay. If Ka is large, is pKa large or small? Small. Small. Okay. Yeah, that's the kind of relationships you'd want to be familiar with. Okay. Where would you use Ka? In any ice table sort of problem, or probably numerous problems, but ice table would be the most common. But if you're given two different acids with two different Kas, the one with the larger Ka will be the stronger one. That's really all I have on Kas.
So pKa is just like pH?
pK is just like pH, or if this is a negative log of X, this would be px. Whatever the item is here, it goes here also. All right. Oh, careful. So, let's see, what should we tackle next? Let's do this here. Let's do pi for a little bit, which is osmotic pressure. Okay, this is really a plug and chug sort of problem. So they would give you everything in here, and you'd find the value that you need to find. The only way that we can make this a little bit harder, but not much harder, is ask you things about molarity. So for example, we'll ask you about moles, or molar mass, grams per mole, or mass. So we give you all the data here, but we don't ask for molarity, we ask for one of these types of things. And what we're saying is solve for molarity and then use that to convert to the units we're asking for. That's essentially what happens. So let's say we give you aluminum chloride, okay? And let's say we have 2 liters of it, osmotic pressure of 5 atmospheres. Let's say the temperature is 25 degrees C. Let's go through a little calculation and let's find mass. Okay? So how would you do that? You would say, well, let's see what I've got. I've got a volume, random. Okay, I got osmotic pressure right there. I've got temperature, but let's change it to Kelvin, 298 K. And I've asked for mass. That means solve for molarity and then go to what you want. So molarity is pi over IRT. By the way, what would I be here? I would be 4. It's the number of entities in solution. So it's 1 aluminum and 3 chlorines. That's how you get it. So a total of 4. 1 aluminum, 3 chlorines. Okay. This is pi, 5 atmospheres. I was 4. R, 0.08, 206. Make sure to use the correct one. I'm using this one because it matched 2 reasons. Really, the main reason it matches by units. But I know that whenever I use something like the ideal gas law, I'm going to use this R, 298K. Okay, that will convert me over to molarity, so I'll get, I just made this problem up, so I don't know the answer, but this is moles per liter. And then what I'm going to do is say, I have moles per liter, I want to know mass, so what I'm going to do is say, well, invert this, moles per liter. I have the volume, it's 2.0 liters, that'll cause the liters to cancel. And then I just look up the molar mass of aluminum chloride, and everything will cancel out nicely. The liters, the moles will be gone, and I'll be left with grams in the end, which is what I asked for, what was the mass. So that's the only way to really make the problem a little bit harder than plug and chug. It's a plug and chug with a conversion. Okay, that's that. Let's go on to approximations. I think that's a good thing to do next. Let's do approximations. And percent ionization. We'll do that all together in one. Okay. And we'll do an example of it in a minute, but just let me write this down. So the approximations go like this. The concentration of the acid, here's one of them, initially, over K, better be greater than 100. If that's true, and this is an easy one to use, especially at the beginning of the problem, because you know both of those numbers. You can almost do it in your head. And this will pretty much work for any weak acid. All right, the other one is the 5% rule. So it goes like this. X divided by the initial concentration of the acid times 100%. This one is not as fun to use initially because X, you don't find that until the end of the problem. So you don't know till the end of the problem if you're okay, but the nice thing about this equals the percent ionization. So usually, as you can see, the percent ionization will be less than 5, so we call it the 5% rule. So this side here is the 5% rule. This side here is the calculation for percent ionization. So the right-hand side finds you percent ionization. The left-hand side finds you if you're within the 5% rule. So it's good enough. Showing that? Yeah, for sure. Okay. Boom, that's it. Okay, that's percent. So this would just be a pure calculation where HA initial will be given. X is found from the end of the ice table when you solve in the ice table. Well, we're crazy going awesome here. Let's do next KP. Let me see if I have an example problem of KP. I might. And if I do, then I have less thinking necessary. Whoever asked KP, did you want like a practice partial pressure problem? So what are you looking for? Okay, that person has disappeared. Oh, hi. Does that sound good, practice? Okay. I don't think I have one, so I'll just make one up. Let's say I gave you this reaction, and they're all gases. Everything in here is a gas. Okay, so I gave you that reaction. And let's say, which one? This one? Okay, it's almost the same. Oh, I like this. I like this. I like this. Boom, even better. It's a problem that's pre-made up. And I have K for it. This is a solid NH3 gas plus H2S gas. And K in this case is equal to 0.18. Okay, what we want at the end of the problem is these equilibrium partial pressures. What's given initially? No information is given. Let's see. I don't see any information given initially. So what does that mean? Again, we want the equilibrium partial pressures. We're given K, and this is a Kp. It's given for this question. There's no information given initially, so what do I put in this first column? I ignore it. It's a solid. What do I put here? 0 and 0. It's nothing's given. Now there's likely a solid in the container, but because I don't have any information about these two, what they're saying is they start off with 0. So it has to shift this way. There's just no choice. There's no way it can go backwards. There's nothing to start with. Also, Q is 0, so it has to shift to the right. So this would be X and X. So Kp is 0.18, which will equal X squared in this case. So all you simply need to do is take the square root of 0.18, and that will equal X. Now what is X equal to? This will, because we're now messing around with Kp, all my units are in partial pressure units, or really I'm working in atmospheres. So this X is the partial pressure of NH3. That was too big. I wanted to subscripted. There. It's also equal to the partial pressure of H2S because they're both equal to X in the ice table. So once you find X, you'll have those two numbers. Another common question they could ask you is what is the total pressure at equilibrium? In that case, you want to find everything that's a gas in the E line, that's equilibrium, and sum it up. And so this would simply be the partial pressure of NH3 and plus the partial pressure of H2S, because that's the only gases here, and that would be 2X. Okay? That's a pretty typical problem. It could get harder if there was more gases, but it wouldn't be harder conceptually. It would just be a little more math to mess with. Cool. Okay. All right, I guess we're left with buffers. We're crushing it here. Okay, let's use this buffer thing. All right. Okay, somebody give me an acid. No, okay, I don't want a strong acid. Acetic acid, okay, we could do that. That's fine. Doesn't matter. You and your friends at home can make up your own acids, you know. H. Yeah, but don't take acid. Okay. Now I need a number. 3 is what I heard first. 17 was too slow, and it's ridiculous. Ka, you can look it up or be given on the test, is this number. Okay? So first, I'm going to start off the problem. I just want the pH of this solution all by itself. Okay? So to get the pH of this, since it's a weak acid, all I'm going to do is write out the acid equation. Okay? And then I need the ice table because it's a weak acid. So I'd put the molarity here. I'd ignore liquids, 0 and 0. Okay, so there's my I line. So you go minus X, and plus X. Again, the minus, it's plus where the zeros are. It has to shift towards the 0. Or Q equals 0 is another way to think about it. It shifts to the right. E is just the sum of the other two lines. So then Ka, in this case, is the acetate ion times the hydronium ion all over acetic acid. All of these are the aqueous compounds. And that'll be 1.8 times 10 to the minus 5 equals X squared over 3 minus X. Is this a good scenario to use an assumption? Crazy, yes. So we're basically saying that X is small, or X will be a lot less than 3. This is what we'll assume. Okay? X is a lot less than 3. How do you know that's good? Well, usually I use the first assumption I gave you earlier. So I check the initial molarity divided by K. So 3 divided by K better be greater than 100. Yeah, it's crazy greater than 100. This is 10 to the 5th, or minus 5th, so it's going to be a huge number. The assumption will definitely work. Okay, so what this causes to happen is this. We just get x squared over 3. Okay, that means x is... Okay, do I have to wait for you all? Will somebody calculate this, or can I not trust you? Oh, nice. What is it? Beautiful. Okay. Yes, x is much smaller than 3. So we can, if you wanted to, you could use the 5% rule here. Where you go, this number divided by 3 times 100. Let's write that out just so, because it's also given the percent ionization, just in case you're curious about that. So that, if you wanted the 5% rule, it'd be this over 3 times 100%. And that's definitely going to be less than 5%. Okay, so we have x. X is equal to what important concentration? The H3O plus concentration. So this is equal to the H3O plus concentration. So pH equals negative log of the H3O plus concentration. Are we expecting a large or a small number? A number near 14, near 7, or near 0? Closer to 0, but not like totally 0. Okay, what is it? 3? Okay, 2.13. All right? So that's a normal, that's an acid. It's not super strong. Super strong would be closer to 0, but it's a fine acid. All right. Yeah. Oh. Oh, good question. Just if this were, okay, if this were a strong acid, hypothetically, what would I do to get pH? I just take the negative log of this number. Done. What is that, by the way? What's the negative log of 3? A negative number, it's less than 0. Yeah, crazy strong. Okay, so, okay, that's cool with that one. Now let's go on. We had acetic acid, right? Let's see. Oh, was there another question?
So, for example, you read at the beginning, you said that it should be a weak acid or base. That's the common.
Yeah. Yeah.
But actually, in fact, they are strong bases.
Oh, you can ask me about it in, the general specific question time. Yeah. Okay. So this was 3 molar. Now let's get a conjugate. This one, I need another number. 4 is fine. All right. There we go. I need another number. 120? Okay, that works. This will be our liter's volume. Okay? So, see, you and your friends can do this at home too. All right. Now, I just added this. With respect to this compound, what is this called?
Ion.
It's a common ion. So it's its conjugate base. It makes a buffer, and it's also a common ion. That's going to make this pH go up or down? Up. When you add a common ion, it's going to go up. By the way, this is a base, so you're adding a base. It definitely has to go up. There's just no other thing that could happen. Okay, now we're going to find the pH again.
Question?
Okay.
Real quick, sorry.
No,
Can it be like approximately the same? Is 1.0 molar approximately the same?
Yeah, oh, the molarities?
Yeah.
The molarities need to be similar. I'd say within a factor of 10 should be fine. Yeah, but they'll usually be closer than that. The closer they are, the better. Okay, so pH. Now, how do I find pH? Shoot. Yeah, I don't want to waste my time with the ice table. Why not use the Henderson-Hausdorff equation? You can use the ice table if you want, but this is just much faster. Okay, pK is the negative log of Ka, or 1.8 times 10 to the minus 5, plus the log of the base concentration over the acid concentration. Okay, whoever's ready, go ahead and calculate that number for me while I get ready for the next part of our monster buffer problem here. Okay, well, somebody's finding that number. I need either a strong acid or a strong base. Okay, I can do that. I need a number. Small number. No. 7 is not small number. I'll go 0.05. Has to be pretty small. Okay, did somebody find this one? 4.8, 6, 4.87. Okay, we can see that the pH went up. That's exactly what we expected, but it's still acidic. Okay, now let's go to the next one. To that solution we just were looking at, I'm going to add this. Okay, what's this? And now I want to find the pH again. Oh, by the way, is the pH going to go up or down? Down. It's going to go down a little bit because this is a strong acid. Well, down a lot or down a little bit, really? A little bit because it's a buffer and it resists pH change. Okay, cool. So now the buffer has two parts. The left side and the right side here, the acid and conjugate base. Which one will I pick to react with this, left or right? The base. The one on the right, the base, will react with the acid. Okay, I have to pick, based on what I have here, I have to pick the appropriate one. This is acid, I'm going to pick a base. Okay, so the acid is symbolized by H3O+. You need to remember that. That's what the acid is. The base here has a K, which I'm going to totally ignore, and I'm just going to use this part right here. Why would I ignore the K? Spectator ion, it's a conjugate of a strong base. It's neutral. I don't care about it. Not for this problem. So, now when I write this out, I'm going to write it out like this. The part of the buffer, the base of the buffer, will react with the strong acid. This will go 100% which way? Right or left? Right. The right, because I have a strong acid. Strong acid drives it to the right. So this will be HC2H3O2 plus H2O. Okay? All right. Now, what the heck am I doing? Let's get those molarities back. The base was 4 molar. The acid was 3 molar. Okay, notice I'm putting something in the product side because I have information about it. And this is 0.05 moles. Okay, I could have used 0.5 moles, whatever. So, the problem is, what do I have to do next? Yeah, I have to think about that unfavored side thing. Okay, now the favored side is which side, right or left? Favored. The right side. So this is the unfavored side. I need a 0 on the unfavored side, and that's what's called stoichiometry. This is going to happen in this chapter whenever you add something to a buffer. So whenever something is added to a buffer. So notice I didn't do it in the previous part of the problem, where I got the answer of 4.87. We didn't do this stuff because I'm not adding anything to a buffer. It wouldn't come up. But here I'm adding something to a buffer. In this case, it pretty much, as far as I know, you'd always have to do this. All right. So I need a 0 on the left-hand side, or the unfavored side, in order to continue the problem. So this is stoichiometry. I need to convert everything to moles. So stoichiometry uses moles. Ice table uses molarity. Okay. So some crazy person gave me 1.8. So I need to go 4 molar. Unfortunately, I cannot do this in my head. Times 1.8 gives me a certain amount of moles. I need that number. What is it? Nice. 7.2 moles. This was 0.05 moles. And then I have 3 molar times 1.8 liters, and that is 5.4 moles. Okay, now I subtract off the limiting reactant, the one that's smaller. Okay, add this up. Oh my gosh, this is 6 point, killing me here. 7 point, even worse. Oh my gosh, 7.15. It looks harder than it is, or vice versa. And this is, oh my gosh, 5.3, no, 5.45. Killing me here. Okay. Did I get everything? I think I got it. All right. What do I do next? I could use the ice table, but I don't want to. Why don't I use the Henderson-Hasselbalch? It's a buffer, right? Again, if you did the ice table, you'd be totally right. You would just be wasting the environmental ink, and PETA would call you, or whatever. So pH, no, I don't think PETA would call you. Negative log 1.8 times 10 to the minus 5, plus the log of the base over the acid. The base is the one on the left, that's 7.15, and the acid's this one, acetic acid 5.45. If somebody got that, let me know. Oh, by the way, why didn't I put molarity in here? It doesn't matter, yeah, you're right. I'm just going to divide by the volume on the numerator and denominator, so you're going to get the same answer. You could have done that, again, whoever, the EPA is going to call you. Because you're wasting ink. Okay. What was the answer? Oh, really? Awesome. The pH on the previous problem was 4.87. Yeah, so it changed very little. If you would have added that to water, the pH would have changed a lot. It would have dropped from 7 way down. But because it's a buffer, it changes very little. Okay, I actually, for the first time probably ever, actually finished everything you guys wanted me to cover. So I'm going to take a little break right now for about a minute. Whoever wants to go can. And then I'm going to stop the video and restart it. And we're just going to do specific questions, whatever those specific questions are.